The main purpose of this video lesson is to show how to prove trigonometric identities, identify the domain and range of the different trigonometric function, evaluate an inverse trigonometric expression, as well as solve trigonometric equation. For this video, I combine all the topics for Module 6 and Module 7. Kindly observe the following guides for proving trigonometric identities. Always remember that in proving trigonometric identities, there is no specific method of proving an identity. We can prove one identity in different ways. And do not forget to write your reason in every step of the proving. Usually, the reason are in the form of the fundamental identities, the different properties of equality, and all the operation involving algebra. For our example, the given is tan theta equals secant theta over cosecant theta. This is in the form of ratio. And in the fundamental identities, the quotient identity, tan theta equals sine theta over cos theta. So there is something to do with the quotient identity of the tan theta. And the cos theta is the inverse of our secant theta, and the sine theta is the inverse of our cosecant theta. So the first reason is given. Next, we will multiply both the numerator and denominator by sine theta cos theta. We will now multiply numerator by numerator and denominator by denominator. And by the principle of commutativity, we can rearrange their order. For the numerator, we have secant theta times cos theta times sine theta. And we regroup secant theta and cos theta together. For the denominator, cosecant theta times sine theta times cosine theta, and group cosecant theta and sine theta together. Why we need to group this? Remember that secant theta and cosine theta are inverses. So if you will multiply these two, the product is 1. Same with the cosecant theta and the sine theta. Applying the reciprocal identities, and since this is 1 and this is 1, we can cancel that. Our expression now becomes sine theta over cos theta. What is sine theta over cos theta using the quotient identity? That is equal to the tan theta. We prove that tan theta is equal to secant theta over cosecant theta. So this is one way of proving this identity. This time, I will show another way in proving this identity by modifying what is in the left-hand side. So I will modify the tan theta and show that this is equal to the secant theta over cosecant theta. First equation is the given. I modify the tan theta using the quotient identity, and the equivalent of tan theta is sine theta over cos theta. By applying the reciprocal identity, the reciprocal identity of sine theta is 1 over cosecant theta, and the reciprocal identity of cosine theta is 1 over secant theta. Since this is a complex fraction, in dividing complex fraction, we will just copy the numerator and get the reciprocal of our denominator. So the denominator becomes secant theta over 1 and multiply these two. 1 times secant theta is secant theta, and cosecant theta times 1 is cosecant theta. We have shown that this left-hand side is equal to our right-hand side. For the second given, prove secant squared theta plus cosecant squared theta equals secant squared theta times cosecant squared theta. Always remember that the first reason in every proving is the given. Also, notice in the given that we are using squared. Therefore, put it in mind that the Pythagorean identities are very useful in proving this identity. By applying the reciprocal identity of secant squared theta is 1 over cosine squared theta. And the reciprocal identity of the cosecant squared is 1 over sine squared theta. After that, we will apply the least common denominator of our left-hand side. By simply copying the denominator, so we have cos squared theta, sine squared theta. Divide this by cos squared theta, the remainder is the sine squared theta times 1, so we have sine squared theta. Cos squared theta sine squared theta divided by sine squared theta, that is cos squared theta, times 1, so that is cos squared theta. The reason here is applying the least common denominator. Observe now the numerator. The numerator is sine squared theta plus cos squared theta. In Pythagorean identity, the numerator sine squared theta plus cos squared theta is 1. This is now our expression. This time, we can factor out 1 over cos squared theta sine squared theta. So the factors now are 1 over cos squared theta times 1 over sine squared theta. By applying the reciprocal identity of 1 over cos squared theta, that is secant squared theta, and 1 over sine squared theta, the reciprocal identity is cosecant squared theta. We have proven that secant squared theta plus cosecant squared theta is equal to secant squared theta times cosecant squared theta. This time, we are going to discuss about the inverse trigonometric functions. This diagram is the illustration of the function. The input is x processed by the rule of the function to have the output y. For the inverse of the function, it is the opposite way. The input is our y, processed by the rule of the function to get the output x. With respect to the variable x, any process of the function is cancelled out by the process of its inverse. If we are given by a set of ordered pairs, to check if this is a function or not, we will just look at the values of our x-coordinate. All the values of the x-coordinate are unique from each other. In this case, the x-coordinate is 1, 2, and 3. Since they are all unique, therefore this set of ordered pairs is a function. How to get its inverse? Just simply interchange the x and the y coordinate of every pair. This is the inverse of this set. Take note that the inverse of this set is not anymore a function because the x coordinate 2 appear twice. Let us consider now the domain and range of our function. In the original given, the domain or the set of all the x coordinates, the set containing 1, 2, and 3. And for the range, the set of the y coordinates is the set containing -1 and 2. And for its inverse, the domain is a set containing -1 and 2, and the range is the set containing 1, 2, and 3. Take note that the domain of the function becomes the range of its inverse, and the range of the function becomes its domain. To verify whether a graph represents a function, we apply the vertical line test. In the vertical line test, every vertical line must intersect the graph at most one point. The first diagram is not a function. Look at the vertical line. The vertical line touches the graph at 2 points. The second and the third diagram are function because the vertical line touches the graph at exactly 1 point. Recall that not every function has an inverse. For the inverse to exist and be well defined, a function must first be one-to-one, that is, each possible output is produced by just one input only. To test whether or not the graph of a function is one-to-one, the horizontal line test is used. If the graph represents a one-to-one function, every horizontal line must intersect the graph in at most 1 point. Consider the second and the third diagram. This horizontal line touches the graph at 2 points. Therefore, this diagram is not one-to-one. And in this diagram, this horizontal line intersects the graph at exactly 1 point. That makes this diagram a one-to-one function. It goes to show that only the third diagram has an inverse. We will now proceed to the different trigonometric function. Let's start with the sine function. Observe the graph of the sine function on the right. By verifying using the vertical line test, the sine function is obviously a function. Let us now consider the horizontal line test. The horizontal line test shows that this is not one-to-one function. If a certain graph is not one-to-one, the inverse does not exist. To get this obstacle, we will always restrict our attention to only a part of the domain of this circular function to become one-to-one. In other words, we will not utilize all the graph of the function. We will just get a portion of this graph to make this one-to-one. The graph on the left is only a portion of the graph of the sine function. It is already a one-to-one function. For the domain of this function, we are using negative pi over 2. And negative pi over 2 is included in the graph until positive pi over 2 and still included in the graph. Therefore, for the domain from negative pi over 2 until pi over 2, values of y, that is from negative 1 until positive 1, and negative 1 and positive 1 are included. Therefore, our range is a closed interval containing negative 1 until positive 1. On the right is the graph of the inverse of sine function, or what we called as the arc sine. The symbol for the arc sine is this. For the domain, the range of the original function becomes its domain of the inverse. So the domain is the set from negative 1 to 1, and the range is the domain of the original function. The set containing negative pi over 2 until pi over 2. Take note of the range of this arc sine because this will be our guide in evaluating the value of our arc sine. By evaluating the values of our range, negative pi over 2 is the same as negative 90 degrees. And positive pi over 2 is 90 degrees. The possible values of our y are from negative 90 in the standard position until positive 90 degrees. And that is situated in quadrant 4 until quadrant 1. Evaluate the following: arc sine 1/2 and arc sine square root of 2 over 2. We will let first theta equals the arc sine of 1/2. And after that, we will apply the function sine. Sine theta equals sine, the value of theta is arc sine 1/2. Remember that sine and arc sine are inverses, so we can cancel that out. We have now sine theta equals 1/2. The interval is from negative pi over 2 until pi over 2. And this is from quadrant 4 until quadrant 1. Recall the asymptote. In quadrant 1, all functions are positive. In quadrant 2, only the sine and its inverse are positive. In quadrant 3, the tangent and its inverse are positive. And in quadrant 4, only the cosine and its inverse are positive. Since the given sine theta is positive 1/2, and our restriction is only from quadrant 4 and quadrant 1, therefore, we will omit the possibility in quadrant 4 because in quadrant 4, sine is negative. Meaning to say, the value of our theta lies in quadrant 1. By folding the 30 degrees, the value of sine 30 is square root of 1 over 2 or 1/2. Meaning to say, the reference angle of the theta here is 30 degrees. And what is 30 degrees in radian measure in quadrant 1? that is pi over 6. Therefore, arc sine 1/2 is equal to pi over 6. We will now proceed to the arc sine square root of 2 over 2. Let theta equals arc sine square root of 2 over 2 and sine theta. Substitute sine and the value of theta, arc sine square root of 2 over 2. Cancel. So the sine theta is equal to square root of 2 over 2. And remember the interval, and since the sign here is positive, surely the answer is not situated in quadrant 4 but only in quadrant 1. The sine theta is square root of 2 over 2. So our reference angle is 45 degrees. And what is 45 degrees in radian measure in quadrant 1? That is pi over 4. Thus, the value of arc sine square root of 2 over 2 is pi over 4. We will now proceed to the cosine function. The graph is situated on the right, and on the left is a portion of the graph of the cosine function which is 1 to 1. For the domain, that is from 0 until pi. So it is still a closed interval consisting 0 until pi. And for the range, that is from -1, and -1 is included, until +1. Therefore, the range is a closed interval from -1 to +1. On the right is the graph of the inverse of cosine function, or the arc cos. The symbol for arc cos is this one. Just interchange the domain and range. Therefore, this is now the domain of arc cos, and this is now the range of our arc cos. Again, this will be the guide in evaluating the value of the arc cos. The range is from 0 to pi, and in degree measure, this is from 0 to 180 degrees. In the standard position, the range is from quadrant 1 until quadrant 2. Evaluate the arc cos of negative square root of 3 over 2. We will let the value of theta equals arc cos negative square root of 3 over 2. So the cos theta is cos of the arc cos negative square root of 3 over 2. Cancel cos and the arc cos. Cos theta is negative square root of 3 over 2. And since the cosine is negative, therefore the theta is located in quadrant 2. Asintan ko, in quadrant 2, sine is only positive. So the cosine is negative in quadrant 2. To have your square root of 3 over 2, so this one, square root of 3 over 2. So our reference angle is 30 degrees. To get the value of the theta, look for an angle in radian measure in quadrant 2 whose reference angle is 30 degrees. Arc cos negative square root of 3 over 2 is equal to 5 pi over 6. We will now proceed to the graph of the tangent function. On the right is the expanded graph of the tangent function, and on the left is just a portion of the tangent function that is 1 to 1. For the domain of this function, that is from negative pi over 2 until pi over 2, excluding the 2 wall, because at these points tangent is undefined because of the asymptotes. So the domain is from negative pi over 2 until pi over 2, excluding the 2 values. So we are using parentheses here. And for the range, since this will extend upward and also this one will extend downward, so the range is all the set of real numbers. We have here the graph of the inverse of tangent function, or the arctan, and this is the symbol of arctangent. So we will just interchange the domain and range. So the domain here is the set of real number, and the range is negative pi over 2 until pi over 2, excluding the 2 values. So if we will get the measure in degree, this is negative 90 degrees and positive 90 degrees. So meaning to say, the values for our arctan is from quadrant 4 until quadrant 1. So that will be the restriction for the arctan. We will now evaluate the following: arctan of 1 and the tangent of the arctan of -5/2. Let theta equals arctan of 1. So tan theta is equal to tan of arctan of 1. Cancel. So the tan theta is equal to 1. And for the restriction, that is from quadrant 4 to quadrant 1. And tangent here is +1. Therefore, the theta is located in quadrant 1 because in quadrant 1, all functions including tangent are positive. And recall in the reciprocal identity that tan theta is equal to sine theta over cos theta. And in quadrant 1, only the angle 45 degree has the same value of sine theta, which is square root of 2/2, and the cos theta is square root of 2/2. Dividing those numbers, the result is 1. What is 45 degrees in radian measure in quadrant 1? The answer is pi/4. Arctan of 1 is equal to pi/4. We will now proceed to the second given, the tangent of the arctan of -5/2. Remember, the tangent and the arctan are inverse, so we can cancel that out. Therefore, the answer here is -5/2. The graph on the left is just a portion of the graph of cotangent function. The domain here is from 0 to pi, excluding 0 and pi. So that is open interval. And the range is the set of real number. And for the inverse of cotangent function, or the arc cot, the domain is the set of real number and the range is from 0 to pi. In quadrant, 0 pi is situated in quadrant 1 and quadrant 2. To evaluate cotangent of the arc cot of -10, just simply cancel cot and the arc cot. So the answer here is -10. This is just a portion of the graph of our second function. In the second function, we have these asymptotes. So this is not part of the values of our domain. So the first set of the domain is from 0 because of this graph. So including the 0 until pi/2, but excluding pi/2 because here the graph becomes undefined. Bracket for 0 including 0 and parentheses for pi/2 because pi/2 is not included. Union with the second set of our domain. The second set is from pi until 3 pi/2. The pi is included, bracket. 3 pi is not included because this is asymptotes, so this is parentheses. For the range, since this will extend downward, so that is from -1 until -infinity. That's why we have this parentheses, -infinity until -1, bracket, because -1 is part of our range. And for the second set, this one, that is from +1 going up. That is from +1, bracket, until +infinity, parentheses. This is the graph of the inverse of second function. So we have the domain and range taken from the original second function. Since this is a union of sets, for the first set, that is 0 to pi/2, and in degree, that is from 0 to 90 degrees. And this is situated in quadrant 1. And this one, pi is 180 and 3 pi/2 is 270. And this is situated in quadrant 3. We are now going to evaluate the value of arcsec of -2. We will let theta equals arcsec of -2. So secant of -2 is equal to secant of the arcsec of -2. Cancel. So we have now secant theta equals -2. So we will identify first what is the quadrant of our theta. For the location of our theta, remember the range for the arcsec, that is either from quadrant 1 or quadrant 3. And since secant theta is -2, in quadrant 1, all functions are positive. So we will omit quadrant 1 for the possibility of the location of our theta. By that, we can assume that the theta here is located in quadrant 3. Applying the reciprocal identity, if secant theta is negative 2, then the inverse of secant theta, which is the cosine theta, the value is negative 1/2. Just get the reciprocal of negative 2, and that is negative 1/2. Remember that the theta here should be in quadrant 3. Cosine 1/2 to that 1. So the cosine of 60 degrees is square root of 1 over 2 or 1/2. Therefore, the reference angle here is 60 degrees. Now, kindly check in quadrant 3, what is the radian measure of the angle whose reference angle is 60 degrees? The answer is 4 pi over 3. Therefore, arcsec of negative 2 is equal to 4 pi over 3.